So my name is Nick Cowan. I'm an astronomer. I'm an assistant professor of astronomy at Amherst College. So I teach classes and I study exoplanets. I have an older brother, and he kind of tried to teach me a lot of science earlier than I was supposed to be learning it in school, and that kind of got me pretty stoked on it. And then as I got older, I very nearly went into engineering and followed in his footsteps. And then a friend convinced me that there would be more women if I became a physicist, and I'd be able to impress people at dinner parties, which was not true. So I went into physics because I was supposed to impress people at parties, and I realized that I didn't really like doing physics. I mean, the people I met were all super nice, but a lot of the problems I worked on were really obscure, and I couldn't explain them to my mom or to anyone really. And then I was actually in the Bay Area. I was at Lawrence Berkeley National Lab because I was thinking I might want to do nuclear physics there. And then there was someone there who mentioned, hey, why don't you think about these exoplanets that people are discovering? That seems a lot more exciting than what we're doing in this lab. And so I said, hey, that sounds reasonable. And so I applied to graduate school in astronomy and got in at the University of Washington. And that's how I got into exoplanets. So an exoplanet is short for extrasolar planet. So it's a planet orbiting some star that is not the sun. So all of our solar system planets, the ones that have names that you know and love, are all orbiting the sun. And exoplanets are all the other planets, the thousands of other planets that we now know of orbiting other stars. Some people have tried to name them, so there are some kind of nascent campaigns to come up with cute names for them. Usually they have really dumb names, so they're sort of like barcodes, and so there's like HD 209458b and 51 PEG and Gliese 581G, and they all have these kind of obscure names. For a while, I've thought this would be a good way to make money, to raise money for doing exoplanet research, and so we could sell the rights, and then of course most of the planets would end up, being Gates 1, Gates 2, Gates 3, but that would be fine if Bill and Melinda Gates wanted to give us hundreds of millions of dollars to do exoplanet research. Then to me that's the necessary evil. In the early days when we first started just detecting exoplanets, they were all the very easiest planets to detect, right? Which basically meant they were the size of Jupiter or bigger and orbiting right next to their star. And so these are by far the easiest planets to detect, and people were discovering these in droves in the early days. Once we built more sensitive detectors to look after smaller planets or cooler planets, we realized that those are actually way more common. And so if you look at the crop that's come out from the Kepler mission, for example, most of those are actually not hot Jupiters. They're not big planets next to stars. They're actually much more Earth-like. They're much cooler and smaller than Jupiter. This is a big can of worms. And so in the early days, so if you go way back when, right? So before we had any known exoplanets, so in the days where there was just SETI, the search for extraterrestrial intelligence, we knew of no extrasolar planets, yet people were out looking for aliens. And if you ask, how did they choose their targets to look at, to try and listen for alien signals? They chose stars that looked like the sun, right? So if you couldn't see any planets, you said, okay, what's the most Earth-like thing we could find? Well, the sun has the Earth, and so maybe other things that look like the sun will also have Earths around them. So those were kind of the bad old days. Nowadays, we can actually discover planets, and we actually can characterize a few things about a planet. For example, we can see how big it is. And so size matters. If you have a planet that's too big, like Jupiter, there's no way, there's basically no surface on Jupiter, right? There's just got too much atmosphere. If you go too small, like Mercury or even Mars, you can't really hold on to a very thick atmosphere. And so that's no good either. And so there's kind of a sweet spot in size. There's a sweet spot in terms of your distance from your host star. You want to be getting enough sunlight to keep your oceans, warm and liquid, and not so much that you boil away your oceans. And that's the start. And then beyond that, it just gets, you can keep coming, the more you look at Earth, the more you realize there's a lot of unique things about Earth. Earth has plate tectonics. It's the only planet that we know of that has plate tectonics. And as far as we know, that's actually important for habitability. So the fact that Earth has plate tectonics and has life on it may not be a coincidence. And you can keep just adding on layers, but typically astronomers tend to focus on features of Earth that we think we can detect from far away. No. I think humans are very myopic. So we're looking for Earth-like planets because it's a decent place to start. and my interest in Earth-like planets isn't actually the life angle, because I figure I'll probably be dead by the time we actually make contact with any critters, should there be critters out there that want to talk with us. I think from my perspective, the reason Earth-like planets are interesting is just because they can teach us about Earth, because they basically are other examples of Earth. And so far we've done our darndest to understand how our planet works, but we've only had this one example. And Venus is quite different from the Earth, and Mars is quite different from the Earth. But exoplanets are so plentiful that there's lots of them, and even in our backyard within 10, 20 light years, there should be many planets that are actually much more Earth-like than anything else we have in our solar system. And so that to me is the kind of the opportunity with exoplanets. So far, it's been essentially a one-way relation. It's been people like me who are trained as astronomers going to geophysicists and planetary scientists, people who study the Earth and the solar system planets, and learning from them. So they're essentially telling us, as far as we know, this is how clouds work, and as far as we know, this is how the mantle and the interior of our planet convects and that kind of stuff. And then we've been taking that and then kind of naively / bravely applying that to extrasolar planets. I think the tables are going to be turning. In some places, they already have turned. So for example, for planet formation, the planet formation theories used to be based entirely on what we knew of our solar system. And 99% of that theory has been completely overturned in the last few decades because of discovery of exoplanets. And I suspect the same will happen when we start actually measuring clouds on other planets. We'll realize, okay, well, we have some ideas right about how clouds work, but a lot of it has just been completely wrong, and it'll be overturned. And so I think in the future will be basically in the future, if you're a geophysicist or someone who studies atmospheric science, I think you'll learn about exoplanets in your classes. Like your textbooks will mention, and it won't just be some throwaway sentence at the end of like the very last chapter, right? It'll be just kind of a basic thing. If you want to understand how rotation, the rotation of a planet affects large-scale circulation. Right now we have some theories that seem to work okay for Earth and maybe for Venus, but they're not like fully cohesive predictive theories. But when we have hundreds of exoplanets out there where we've observed their atmospheric circulation, then suddenly that'll be something that there'll be entire chapters explaining, okay, this is what we've learned from exoplanets about how atmospheres work. And I think that'll trickle down, and eventually we'll be learning about planetary surfaces and planetary interiors. That's trickier, but there are some indirect means of learning even about that for exoplanets. So there's these hot Jupiters. So hot Jupiters are these big gas giants orbiting right next to their star. And when we first started looking at these planets, we noticed that they all seem to be black. So they were like black, like a charcoal briquette. Like they basically absorb everything every photon that hits them is absorbed. So they glow red hot because they're hot. That's why we call them hot Jupiters. But if you look for reflected light, you don't see anything from them. And that was sort of the status quo for about 5 years, which is like forever in this field. And then we discovered one planet that appeared to be really shiny. So it was actually reflecting a lot of light. And so we said, okay, well, this planet seems to be cloudy. And then what we did is we actually mapped out where the clouds were on the planet by watching the planet for a full orbit with the Kepler spacecraft. And what we noticed was that there were clouds on this planet, but they weren't evenly distributed everywhere on the planet. So the clouds were only on the western hemisphere, and the eastern hemisphere was cloud-free. And so that's pretty crazy. And there's no example of that in the solar system. I mean, there's no planet in the solar system that has like some weird asymmetrical cloud pattern like that. And so this is something that we're still struggling to understand now.